Herbert, CBE, FRN, is the manager of the EDSAC replica project. Before retiring, he was the chairman of Microsoft Research for the EMEA region, with his main base in Cambridge, where he followed in the footsteps of Roger Needham. He's going to talk about the context in which CAP was designed, explore the latest aspects of the novel aspects of the architecture, and show how CAP ideas have influenced more modern systems. He's also going to explore some of the very Cambridge quirks. And on the human side, he's going to talk about the respective roles of Maurice Wilkes, David Wheeler, and Roger Needham in the leadership of the CAP project. Thank you.
Thank you, Rachel. So the CAP project started in about 1970, and the machine finished its practical life in about 1986. I came on board in 1975. So anything I talk about pre-75 is slightly conjectural folklore. Well, I see John Horton is in the room, so he can correct anything there. And if we do have disputes, we're getting the movie today. I have the book, the manuals, my thesis, my lab notebook, and if you're really desperate, the operating system sources and the microprogram source are on my Macintosh. So I feel well armed. The gods are making all the appropriate noises that I should have the temerity to present on CAP. And I was a research student working on the project during that period. I actually put this slide up, but it's in the middle of the presentation. Let me go back to the beginning. So the Cambridge CAP computer. As I think is well known, the mathematical laboratory, which these days calls itself the computer laboratory in Cambridge, had a tradition of building its own computers from the earliest days, starting with EDSAC, designed in 46, operational from 49 onwards, on which I'm now working with Chris Burt and others and building a replica. And we describe it as the world's first practical computer. Anyone who is working on these early machines describes it as the world's first ... computer, and you have to pick your unique ... We say practical because the tradition in Cambridge, if you have a tradition when you start the first machine, the focus was building something for people to use rather than getting lost in the weeds of designing computers for their own sake. And then when we come to CAP, you might see we lost sight of that because by then the computer lab had an academic department which did most of the work. After EDSAC 1 came EDSAC 2, which I was reading a description of that, a paper someone wrote the other day, which is described as a beautiful but rather slow machine. EDSAC 2's claim to fame was it was the world's first bit-sliced machine, which most modern parallel machines are, and it was the world's first microprogrammed machine as key innovations. And so an important part of the Cambridge tradition was not only building machines that could be used by users, but looking for technical innovations to make the machine more reliable, more effective, and so forth. The nightmare with EDSAC, as I'm discovering with the replica, is almost every chassis does a different job. So if you want to have spares, you've got to have a spare EDSAC. The advantage of going to a parallel architecture and a bit-slice architecture, as EDSAC 2 did, is you only need one spare chassis, and if a bit dies, you replace it with a spare, and so the maintenance is much easier. And since more of the chassis are identical, it's easy to fix them and have test equipment and so forth. So there's clearly a lesson learned there. The successor to EDSAC 2 was Titan. As we heard in the last talk from Simon, Titan was in some sense a stripped down or simplified or under-resourced Atlas. And indeed, when I arrived in the computer laboratory as a young PhD student in 1975, Titan had been turned off for a couple of years. Everyone was using an IBM 370-165, which seemed to be regarded by most of the users as a large step backwards. Other people like Barry Landy were labouring hard to get the 370-165 to do the kind of multi-access things that Titan had done, and indeed accomplished their role in doing so. Titan was the last Cambridge machine that was built to serve the university as a whole, and with the focus on building a service machine, and with all the pressures that has of keeping the machine operating 24/7, not introducing new features into the operating system that undermine working programs and so forth. When we come to CAP, the story has changed. The computer laboratory had essentially broken into two halves, and they were fairly autonomous. The computing service that carried on providing computing facilities for the university, based around its 370.165, led by David Hartley as the director of the computing service, and with its own team of program development staff, people like Barry and others, who maintained that system and developed software, system software applications for it. And what in the other university would be called a computer science department, that essentially was academic. It had a master's program, the Cambridge Diploma. It had just started teaching computer science as an option in natural sciences tripos. And by 1978, when I finished my PhD, there was actually a Cambridge 3-year computer science tripos. And so that was a period of transformation. In fact, I got to Cambridge by the fast route because fortunately there wasn't an undergraduate program in computer science in 1972 when I was picking universities. And much to the chagrin of my headmaster at my grammar school, I told him that rather than trying to do chemistry at Cambridge and taking an extra year to do the entrance exams, I was going to do computer science at Leeds, because I thought computing was far more fun than chemistry. He was pretty upset about that. And I remember interesting conversations, which basically boiled down to the fact I was ruining his batting average against the grammar school in the next town about how many kids they got to Oxford and Cambridge. What my interests and career prospects might be were completely relevant. And so I had great delight going back to an old boys reunion 3 years later and saying, I'm at Cambridge now, Mr. Hicks, doing computing as a PhD. It only took 3 years, but I didn't have to do the scholarship year. So there you go. So CAP was built by the academic side as a research project investigating the ideas of capability architecture, which is what most of this talk will be about. Although actually within the academic half of the computer laboratory, it did run as a service machine. And I don't know how much time I'm going to have for all the anecdotes, but if CAP hadn't existed, we wouldn't have had C++. I'll let you form your own conclusions about that. Jan Strustrup was a research student who used CAP at an early stage in his research career. When I gave the blurb for the talk that Rachel graciously just read a moment ago, I described CAP as the last computer that Cambridge built. And then as I started to write the presentation, it's always dangerous to write the presentation after you've written the abstract because you're a bit constrained by what you've promised to say. I realized that actually we were still building machines well into the 80s, because what came after CAP was the Cambridge Distributed System, which was, well, this modern day and age, you call it a cloud computing system. The idea was you had a network that connected users at terminals to processors that were somewhere out there across the network. You said, run this program for me on this data, described using, well, actually network capabilities. We got the idea from CAP. And to build that system, we did build a lot of kit ourselves. Simple microprocessor servers for things like print servers and terminal concentrators. The processor bank was built out of Motorola 68000s. There we go. These things in crates, these were all built in the laboratory. The ring itself was built in the computer lab, and indeed CAP got connected to the ring. So actually, in terms of the last machines built in the computer lab, probably Cambridge is, CAP is the last but one rather than the final. It's all a matter of definition. So that's the, if you like, the progression of Cambridge machines. And certainly, having listened to the talk about Atlas at the last one of our meetings, and knowing the Titan system at Cambridge, although I never used it, it was very much part of the culture in the field at that time. There's an awful lot of Atlas come Titan in CAP in the instruction set and the way we thought about things. The key players in the CAP project were Maurice Wilkes, head of the computer laboratory, and obviously leader of the EDSAC and the EDSAC 2 projects, Roger Needham and David Wheeler. Now, the time the CAP project was kind of really progressing, that 75 to 78 era, when I was a research student, Maurice was getting close to retirement. With the split of the computer lab into the service and the academic side, a lot of his time was taken up with growing the academic department, fitting that into the university structure and so forth. And as a obviously eminent figure, he was involved in many political things. So he had a lot of time outside the laboratory. He was involved in the initial conception of the project and some of the first design decisions, but by the time that the machine actually got built and people started writing an operating system, his involvement was entirely superficial. I don't remember him coming to more than a handful of project meetings during the time I was working on the project. I do remember working with him and Roger in 1980 to writing that book. I was their sub-editor. They kindly gave me an appendix at the end. And a lot of my time as sub-editor was spent explaining to Wilkes how CAP had turned out, and him saying, that wasn't what I intended. No, Professor Wilkes, but that's what we built and that's what you've got to document. Harumph, you could say, his own way. And Roger, being Roger, would just let me loose in that lion's den because that was a fight he didn't want to have. And this was a period of transition. By the end of the CAP project, Morris had retired. The university insisted he had to retire at the age of 68. He got off to work as a consultant for digital. I think an excellent model for a senior person retiring. The best thing you can do is bugger off and let the next guy get on and make his own mess and not be there like a ghost on the landing. And so Morris had gone by the end. Roger was head of department. Roger certainly led the major software development of the project. David's role was he designed the hardware. In some sense, it was done mostly as being supportive of colleagues. There wasn't a great deal of innovation in the CAP hardware. It was David's first project using integrated circuits. Previous machines have been valve or discrete transistor machines, and I think it was him getting his head around that technology. He used it fairly conservatively. The aim was to build a machine that we could get on with experimenting with the software, which is where the real research goals were. His luxury was, while everything else was essentially specified by Roger and the students who worked on the early architecture design, David was given a free hand on the floating point unit. And this was slightly before the IEEE laid down what a floating point unit has to do. And if you let a hardware designer with David Wheeler's talents loose on designing a floating point unit, you end up with one that's 10 times more powerful than your basic computer. It is completely unprogrammable. And the thing which, unfortunately, the thing which is lost, there was a wonderful 2 sides of A4 description machine that David produced, which was a marvelous mixture of waveform diagrams, bits of circuits, occasional logic summaries and truth tables that told you all you needed to know. If you scrubbed any one thing off that sheet, you would have incomplete information. There was nothing on there duplicated. We've lost that, and that was the only documentation we had of how the floating point unit actually worked. So all we have in the documentation that survives is how to make it do the floating point arithmetic that we used for most of the programming languages on CAP, what the unit was actually capable of, and as we power it up again and start poking around and look at circuits, no one will know. And so for David, it was, I think, a fun project. He was learning a new technology, but not necessarily very intellectually stimulating, and so his fun was to build the floating point unit for us. Surrounding those three was a cloud of research students, several generations. The first generation essentially designed the machine architecture. The second generation, of which I'm an example, wrote the operating system. And the third generation went round and did the second system and designed different architecture and different operating systems and so forth in the classic way. Cambridge's style very much was to rely on research students to do the work. Unlike other places, for example Newcastle, that hired lots of research assistants as paid staff, using research students is a mixed blessing, and they're cheaper, so you can have more of them. But they have got to produce a thesis, so they do insist on having a bright idea rather than building what you want, and then they disappear and write it up for 2 years. And so it's a nightmare from the project management point of view. And there are bits of CAP that suffer from too many bright ideas. One thing that did survive, when I appeared as a research student, we all lived in one of the rooms in the lab called Room 208, and we subscribed to the Beano comic for amusement. And one of our members, a guy called Des Watson, cut and pasted bits of the Beano to write the prehistory of the CAP project. And this is the first slide. I'm sure many of you remember the characters in the Beano, the slightly inept teacher, the rather overweening head, and this gang of rather unruly kids. So here we have on the slide, I put my little marker down. Here we have the teacher, who looks very much like Roger Needham. You recognise the glasses. Who heard about these things called capabilities. I shall go and tell the head of our new project, I'm going to build a capability machine. It's a wonderful machine. We can make it do all kinds of clever things. Here we have the headmaster, Maurice Wilkes, getting very excited. The teacher asking for volunteers and lots of students lining up. And the students saying, you lot are going to write an operating system. And there's several pages of this. It's so full of in-jokes that I would bore you to death if I went through. But it's a wonderful reminder of the history from the time. And certainly, looking back at it now, I can still recognise who is being parodied by which character in the Bash Street Kids. And absolutely every one of the Bash Street Kids has a corresponding research student. It's an amazing coincidence. So, just to kind of pull all that context together, we had the split. Titan had gone to the computing service and been replaced by the IBM. The big question for the people who had a background in systems, like Roger Needham, Martin Richard and others, who decided to go to the academic side, was what to do as their next major project. It was obvious all future computing service machines were going to be procured commercially, and so it was necessarily going to be an academic project. Roger was becoming established as the leader of the systems research group. It was one of the largest research groups in the lab at that time. There were some surrogate things. A legacy of those earlier projects was the computer lab had a very large engineering workshop to keep busy. A full-function mechanical workshop that could make the kind of ironmongery you needed for machines of the 50s and 60s. Electronics workshop staff with instrument makers and wiremen and so forth, who'd been required to build and maintain those early machines, all on payroll. What the hell did we get them to do? All they could be offered on the IBM machines fixing teleprinters. That's not really very stimulating stuff. And so doing another hardware project was quite important to keep that crew busy. And at the time we're talking, in the early 70s, that's when Research Funding Council for Academic Projects of Scale came through. And so that made a degree of sense. A bullet I guess I could have added was there's always a little bit of Cambridge-Manchester friendly rivalry. Manchester were charging off down the path building MU5, and so Cambridge couldn't stop building computers and let Manchester get away with being the only acting town. The motivating factor for the architecture of CAP, if you like, the previous slide was why build a machine. This is now why choose the kind of machine CAP turned out to be, and these capability ideas came from the experience of writing operating systems in the 1960s. In particular, the Cambridge experience of writing the Titan operating system. That was a full-function mainframe operating system with multi-access, terminal access, spooling of devices, blah, 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 all the kind of stuff you'd expect and you saw in comparable systems like George, the evolution of the IBM systems and so forth. The nature of those was they were written entirely in assembly code. As we know, assembly code is somewhat error-prone because you're working at a very low level and you're working in the world of the machine rather than the world of the application you want to build. Typically, there was a monolithic supervisor that contained most of the operating system, and then users ran in user processes that were in some way separated in their address spaces. And so you'd have a supervisor mode and a user mode, some sort of memory protection to stop users scribbling on each other and scribbling on the operating system, typically just a base and limit of where your bit of memory started and how much of it you could have, and separate people in that way. The supervisor could typically access all of memory, and so bugs in the supervisor could destroy user programs as well as destroying itself. And you would typically have that the supervisor made up of some very trusted kernel, perhaps some batch of privileged system processes that were allowed to access devices and do things that user processes couldn't, and then the user process on the outside. The problem with that style of operating system development, as operating systems got larger and more complex, was essentially corruption stored by programs running amok for one reason or another. Classic ones were address validation. If you passed an address from a user program to the operating system, you had to translate it from the virtual address the user had to the absolute addresses the operating system used. If you forgot to do that or got it wrong, you ended up scribbling in some random place. All the classic buffer overruns that plagued my last employer's operating system, of people just forgetting how many fence posts there are. If you've got n gaps, you've got n+1 fence posts. We all got that kind of mistake in our loops. Uninitialized pointers falling off the end of lists. In an operating system, all that gets worse because you've got race conditions, you've perhaps got 2 or 3 parallel threads working on the same data structure, something putting things in a buffer, some things taking things out. If things happen in the wrong order, your pointers get left a bit garbled. Or just old system state lurking around. Some user process is hanging onto a buffer that the operating system thinks it's giving back and giving to someone else, and random things happen. All that kind of stuff made systems crash, and any of us who use 1960s design, 1970s operating systems remember all that kind of thing, and the whole system is extremely fragile. So what are the possible solutions? Well, in the late 60s, early 70s, there were essentially 3 ways you could go. The first, which was seen as very academic and conceptual, although in the modern day and age actually is probably the practical thing to do, is to write the operating system in some super highly typed, very safe programming language where you can't make those kind of mistakes. In this modern day and age, you had software verification for that, theorem proving, blah, blah, blah. And indeed, one of the things the Microsoft Cambridge lab did when I worked there was write a theorem proving system to check that third-party device drivers can't crash Windows, which is why you don't see so many blue screens anymore. Because most of the blue screens in Windows were inflicted by other people's device drivers on our operating system, rather than our operating system tripping over its own bootlaces, although we could try to do that occasionally too. So you could think about using a strongly typed language. And at the time, probably the most strongly typed language around was Algol 68, and indeed there was a group in Cambridge who were writing Algol 68 compiler, and to help them along we used Algol 68 as our systems programming language, and that turned out, with hindsight, to be a sort of stupid decision, and I explain why when we get to the end. It basically took away the question that we were trying to answer about building more robust assembly-coded operating systems. If you write in a high-level language, you just remove the problems you're trying to protect yourself against. The other option was to prove the system secure, and certainly people were doing that. The Stanford Research Institute had a provably secure operating system that had a tiny kernel that enforced protection, and that was proved correct and did all the isolation, and that found its use in various military contexts. In the hardware world, people were generalizing the idea of supervisor mode, user mode, into the idea of protection rings. And the paradigm system of that is Multics. That's an image of a Multics carpet. It's the only Multics image I could find on the internet that had pictures of rings in it. And the kind of idea is you have these layers of rings of increasing privilege as you work your way into the middle. So at the very core, you'd have the kernel operating with full access to everything. Around that, you write the operating system in a ring. It can't interfere with the kernel. It's got some privileges, but somewhat reduced. And then you put subsystems like your record management package, database system in a kind of next ring out. That would still have privileges that users haven't got. And then you put user processes in the outer ring. And basically you have fewer and fewer privileges. This model was copied, for example, by ICL in their new range, and if you look at what Intel processors, essentially the same model is there. You've got big 4 protection levels. The sad thing about that is systems don't naturally layer. It turns out they're more complicated. There are things that might look like subsystems to users, but if you're building a record package, for example, you might want to do low-level buffer management and disk optimization, and so you've got to start breaking the layers, and it all falls apart. Multics struggled with that, and indeed the Multics project at MIT, towards the end of the life of CAP, went through a rebuild of their operating system to build a secure Multics and enforce the layering, and found they essentially had to virtualize their system and run a Multics on a Multics to get the security guarantees done. So layering didn't work either. So the bright idea on the streets in the late 1960s, early 1970s were these things called capabilities. The earliest paper by Jack Dennis and the student Hazel Van Horn in '66, Butler Lampson wrote about this stuff in '69. And the idea of a capability is it is an unforgeable ticket of permission to use some system resource held by a user. Lots of implementation questions in that, but basically you've got some bag of bits that you can exhibit to the machine that says I'm entitled, for example, to access this piece of memory, or to call that subsystem, or to use that device. And with those tables of permissions, you essentially can give each piece of the system the minimum set of privileges it needs to do its job. and you can pass privileges from one system to another. So if I want the file system to read some data for me, I pass it a capability from my buffer, it writes in my buffer, I take my capability back, I've got my buffer back, and so you've got the kind of protection. It's a direct contrast. Essentially, you're giving all the privileges to users who hold this collection of tickets or capabilities in their hands with what we're familiar with in modern file systems of access control lists. With an access control list system, you label every resource with who can use it. The problem with access control lists is you have to know in advance who all the users are, or you have to have wildcard patterns and notions of groups like public or all systems users or whatever. And anyone who's tried to manage, for example, a Windows NT file system at scale knows what a nightmare it is if you don't know in advance who all the users are going to be. And you tie yourself in knots of groups and subgroups and how privileges propagate and so forth. Both actually are encoding access control matrix, which has, if you like, subjects down the rows and objects across the columns, and X says this subject can access that object. The whole access matrix for a large system would be too huge to hold in memory, so you have to encode it one way or the other. And essentially, Multics and the ring-based people went down the access control route, which is encoding the columns. Every object says which subject can use it. The capability crowd went along the rows. Every user had a list of which objects they had access to. You've got a problem. If these tickets are going to be unforgeable, ultimately they've got to be something in memory that ordinary programs can't change, otherwise people will write their own tickets, you'll be open to forgery. So there are essentially 3 ways of doing it, only 2 of which have been invented in 1970. This is always a challenge of writing a retrospective talk, because you know the right answer, which you didn't at the time when you were doing the work. You could tag the memory and say this word is a capability, this word is ordinary data, and not allow people to scribble on capability words. And the ILIF basic language machine is an example of that for some of the Burroughs architectures. You could do what CAP did. You could have a segmented memory, and you can label segments as either containing data or containing capabilities. We didn't allow segments to be mixed. And you can have additional instructions in your instruction repertoire that let you move things around in capability segments, so you can copy capabilities from one person to another. And most of the rest of the talk is about capability segments and capability instructions. The later idea that came with networking and with Roger's invention is you can encrypt the capabilities using a secret key, and then only people who've got the decryption key can decrypt them. And you just send them around as bit patterns, and then you can store them in any old memory. All you've got to do is protect the keys, so you've somewhat changed the problem. And in the networking world, that makes a lot more sense. The second concept we need to introduce to be able to talk about capabilities coherently is the idea of a protection domain. And this is the unit of system structure. When I talked about early operating systems, I basically talked about kernel and processes as the sort of large units, and the process typically was an address space, and was a unit of scheduling, and so forth. We want something finer grained if we're going to do minimum privilege of these capabilities. So leveraging a number of ideas that were current at that time, Dave Parnis had written on the idea of modules. This is the time when modules in software was a new idea. It couldn't all be one monolithic program, it could be broken to pieces. Mike Schroeder, MIT, had been talking about mutually suspicious subsystems in operating systems. They have to use each other, but they don't trust each other. That's kind of, in fact, he was a Multics student, and he fell over some of the layering violations that they had in their system. People at Carnegie Mellon University talked about similar ideas of separating policy from mechanism. You wanted to build bits of operating system that implemented mechanisms like virtual memory, but you didn't want to build in a particular page replacement policy, for example. You might want different policies for different environments. And the whole thing had got wrapped into separation of concerns and minimum privileges. So we can describe privileges by a set of capabilities. You can only do the things for which you have the capabilities. And if you want to do something else, you need to move to another domain that has the privileges to do the thing you want to do. If, for example, you want to write a file, you need to move to a protection domain which has access to the disk, and you might want to pass across some temporary privileges for access to your buffers. The file system domain reads and writes the disk, puts your bits on the disk, and then comes back to you and says, job done. And so you've got your file written, but you've not had to interfere with the disk yourself, and so the disk has been protected from users doing aberrant things. In CAP, we called these things protected procedures. The model was inside a process, there would be a protection domain, you called them in the same way you call subroutines in programming languages, and as you entered, you picked up the privileges of the new domain, you discarded the privileges you had, there was essentially a stack. When a procedure went return, you came back to the environment you were in before. You could do it that way. Some other capability architectures used inter-process communication as domains, and essentially went for lightweight processes. My own version of CAP, I did a revisionist CAP, used inter-process communication for doing that. The best known example today is the Mac operating system, which is what underlies Mac OS and Macintoshes. That's a capability architecture, but all done in softwares. And in fact, done by my former boss at Microsoft, Rick Rashid. So that's kind of the background. Let's start talking a bit about CAP. It's a 32-bit machine based on Titan. Yes, Titan was a 48-bit machine, but essentially it's, if you throw away enough bits, you end up with CAP. At the time I'm describing the machine, when it was being built, it had 192K of store, which as a young, spotty research student seemed a huge amount. I'd never seen more than 16K in my life before that. 64K had come from Titan. It was quite fast interleave store. 128K was some core store made by Philips with an awful cycle time. Goodness knows where the lab got it. It must have been cheap. To try and make the thing run quickly, we had what in this modern day and age would be called cache memory. In Cambridge style, they were called slave stores. We had 2 read slaves of 256 words, and we had a write slave of 32 words. And so the idea was the working data would end up being caught by these slaves. You had 2 slaves, so it turned out you had 2 locations that hashed at the same point. Essentially, they would flip between which of the slaves they were in. And the write slave would capture writes back to store, and then the words would dribble out from the write slave into the slow store if that was where the ultimate destination. And provided you didn't write to the same location again before the words finally got out there, you were fine. And so the slave stores work quite nicely, although by modern standards they're ridiculously small. And indeed, one of the CAP's challenges all the way through is because it was built when integrated circuits were still at the level of AND and NAND gates, you couldn't get large memories and so forth. We just couldn't afford to build large-scale memories and so forth, and so everything's a little bit too small. It was a microprogram machine. How else would you do it in Cambridge? With 4K of 16-bit words from the microprogrammer. It's great fun. We're living in a 16-bit world trying to program a 32-bit machine. Prepared me well for living in Windows as we transitioned from 32 to 64 bits. Been there, done that, got the t-shirt. I've talked about the floating point unit. The machine itself only had 2 peripherals, a paper tape reader and a teletype. The paper tape reader to read in a bootstrap program, and the teletype to print out a diagnostic message that didn't work. We used the CTL Modular 1 as essentially a front-end processor, and that had all the real peripherals like disks, line printers, paper tape stations, and so forth on it, because there was no interest from a research point of view in writing and building all that stuff. So we had a channel out to the Modular 1, and you asked the Modular 1 to do the low-level I/O for you, and that was in the microprogram. Later on, all that was replaced by Cambridge Ring services, and CAP ended up literally being a processing server, a processor and a memory and network interface. Even its file system moved across the network. Instruction format, very boring. A function field, 2 index registers, BA and BM, and 16 address bits. Typical instructions, BN says register BA, whatever number is in there, becomes equal to the contents of memory location BM, treating that as an index register, add those bits N to it. So typically in the index registers you keep the base address of a vector. This would pick up the nth word in the vector, put that into register BA, that's a nice simple one. Instructions might update store, BBPS, B becomes B plus S. Then you take the register, would be the original contents of the register added with the contents of that location in store, or added with literal. You could write the results back to store. We had exchange instructions, and this exchange is stored with a B register, so the B register becomes equal to the contents of store, the contents of store become equal to the B register. Very handy for operating systems people to have those kind of instructions and atomic instruction. It's how you can do test and set type things. whole lot of others, shift instructions. Old Cambridge ideas take a long time to die. In EDSAC originally there was no B register. So the way you did indexing was you updated instructions slightly before you fell over them. So you'd add things to the address field and then you execute the instruction. Well, self-modifying programs were clearly a bad thing by 1968, 1970. So we had official ways of doing it. We had modify instructions that said, modify the next instruction with this data. So rather than updating the instruction in store, this essentially did it through remembering in the microprogram the next instruction has to be tweaked. And so it meant your programs could be read-only, it was good from a protection point of view, but you could still write self-modifying code. And so that was a good source of examination questions. Design a computer with read-only memory that can execute self-modifying programs. And any student who read the CAP manual was home and dry on that one. All the usual things, jumps. Because we were defining the machine entirely ourselves, we also put in instructions for high-level languages. srefn is actually Albel 68 BCPL subroutine entry. We don't really understand how it works. And the case statement is the BCPL switch on the Albel 68 case. So we had some of the kind of creep that happened in 1970s instructions, putting ever more complicated things in there so that the microprogram do the heavy lifting. So that was the instruction format, very like typing. The system architecture, the model of the machine was there would be a hierarchy of processes. Analogous to the kernel or the supervisor in early machines, there would be something called the master coordinator that owned all the resources of the machine. It could have sub-processes, which were independent address spaces with their own sets of capabilities, which were subsets of what the master coordinator had. So the typical idea was you'd have a capability of all of memory up here, and you chop out memory for each of these processes by essentially segmenting that. You could enter a sub-process in master coordinator with an ESP instruction. This thing would execute. The master coordinator could schedule between these so they could run in parallel, and they could find their way back using the enter coordinator instruction. At the time CAP was being designed, there was often a few of them were virtual machines. IBM had done VM360, what Brian Randall and others had done, and CAP kind of caught that disease, and so it decided we ought to have sub-processes too. And I think some of the thinking, though it's before my time, was there would be the master coordinator, some systems processes, one of which would be the user process supervisor, and user processes would hang off that. And if the system could have sub-processes, then users ought to be able to have sub-processes. Kind of anticipating ideas like user threads that we have today. But unfortunately, the mechanism was all far too complicated and expensive to actually use it in that way. I think I am the only person with the ESP down to the next level to write a demonstration program to prove it could be done. And it worked. Inside each of those processes, your address space was described by a set of capability tables, which were segments in memory containing sequences of capabilities. So when you constructed an address for one of the instructions, the address would be 32 bits long. There would be 8 bits of a segment number, which said which capability segment was being referenced. 8 bits of an offset that would count down that capability segment, select a capability, and that capability would describe an area of memory. And then the index would be relative to that. So essentially you had virtual addressing, because obviously all this would be mapped to absolute addresses somewhere else. These were virtual addresses, the capability gave you the absolute address, you added the index to it, and then you knew what to send off to the store. So fairly straightforward segmented addressing. It's a 32-bit sparse address space. You don't have to completely fill the capability tables, you can have holes in them. And that was really quite useful. It's the first time we had a very large address space, which really helps you with high-level languages. Systems that have small address spaces are really a nightmare from that point of view. Another Achilles heel, though, we had segments, but we had no paging. That, I think, was a Titan legacy. Titan hadn't had paging, so why should CAP have paging? But unfortunately, by the time we were using CAP, programs had got longer and segments had got longer, and it was painful. So an unfortunate decision. How did the capability get resolved? This is where you have to tie together that process hierarchy picture and the addressing picture. So here we've got a process at the lower level, and here we've got the master coordinator at the higher level. Both address spaces, with their sets of capability tables. The magic step is a sub-process has a thing called a process resource list. So its capabilities and the capability segments relate to a list of resources which you can think of as higher level capabilities. And those are defined in terms of the capabilities of the parents, which are defined in terms of what's in the master resource list, and that's actually where you find the absolute address. So working the other way down, in the coordinator, you could have a capability here that, for example, describes all the memory from location 0 through to 192K. You could slice out a subset of that as a capability here to be the memory for this process. And then that comes down here. You could subslice that to be the individual capabilities for how you want to map your address space across memory. So a lot of flexibility. What the microprogram had to do was when you resolved an address, you end up touching these capabilities, it would have to run through all these chains, calculating essentially the absolute address of the location you were trying to touch, making sure you hadn't violated any of the size fields in all the capabilities going up there, and also checking the access rights, because you might have read-write down here, but only read up there, because they have to be refined. So quite a complex task for the microprogram to involve itself in. And just to kind of show that again, take that previous picture where the process structure is more visible. This is how it looked in detail. The low-level capability has some access bits, a relative base and size to its parent, which is in the process resource list, that had its own access bits and relative base and size to a capability in the next level process up, access base and size relative to the master resource list, where hey presto, you had an absolute address and a size. And so that was the process. And if you did the nested sub-process down to lower levels, that structure could go on indefinitely. There was strictly no limit on how many ESPs you could do, but there was a hardware constraint that said after 64 the machine would just loop indefinitely. Access control, essentially on memory you had read, write, execute permissions, the kind you might expect on data. Also read and write capability, which is how you distinguish capability segments from data segments. You would very rarely find a segment that had both data access and capability access. Typically that would only be in some very privileged part of the system that was allowed to manufacture capabilities out of thin air. That's obviously the core of the protection system. And there were capability instructions in the instruction architecture. You could move a capability from one place in the address space to another. If I jump back, you could, for example, move that capability from there to that place in that capability table. And when I talk about how we change protection domains, you'll see why that's actually quite a useful thing to do. So you could remap the address space, you could change the access controls and the base and limits, and you could ask questions about capabilities and capability tables through those instructions. And I actually had to go back to the microcode to find out what move cap A did, because I don't think we ever used that one. So now let me talk, that's kind of got the basic addressing inside a process sorted. Now we need to put protection domains inside those processes. This was done using something called an enter capability. And an enter capability described a protection domain. So essentially what has to happen when you enter this new protection domain, you put down your old capabilities and you pick up the new ones in the new domain and you jump to an entry point in the new domain. That's the gist of it. So you would have a thing called an enter capability, and it shouldn't have base and size in it. You can see where cut and paste has gone wrong. That error is not in my thesis, because my thesis was done in Letraset. In Letraset, you don't make those kind of errors. Because you can't cut and paste, and the economy of effort means you think before you stick anything on the page. So there was just some access bits, as we've got here, I keep losing this thing, and an index up to the process resource list, and that should say PI and R. I really did get the cut and I was doing this a bit late at night, wasn't I? What you had were 3 entries that told you the indexes elsewhere in the resource list for 3 capability tables called PI and R, and I'll explain the names later on. And essentially what happened on the enter instruction was you put on a stack the current PI and R capability tables, you loaded the new ones into the address space, you picked up one called N, and it became A in the new world. The next picture explains that. You remembered where you were, and you would jump to address P00 in the new domain. You always came at a well-defined entry point. You couldn't break into the middle of these, otherwise you could make them execute arbitrarily. Magically, there was a return instruction that would unstack the previous PINR, get you back to where you were, move back the capability table called A that you passed across, so there's a kind of buffering thing going on there, and pick up your say B15, and you would continue. And finally, there's a machine instruction called make in directory, which should be called make capability table, that makes you a new capability table of a given size. So kind of carry in your mind the fact there are these three capability tables, P, I, and R, which are described by the enter capability, and those describe the capability tables, the capability segments of the new protection regime. And let's do it by some pictures. So there's our enter capability. I've got three tables, P, I, and R. I can have others in my protection domain. One of those might have an enter capability that comes up the process resource list, and that describes the P, I, and R of the new domain. There's also a stack lurking around in the background in the hardware. It's called the C stack. I'm not going to expose too much detail about how that was worked. So that's kind of the starting condition. I'm in this domain. I want to invoke that domain to get something done. I'm a user. This is the file system. First thing I do is call that making instruction. That magically creates a new empty capability table for me. It's called the A table. Each of these corresponds to number. P was 4, I was 5, R was 6, A was 2, I think. And this magical C stack, which is a process resource, was where the space was carved out for that and the pointer moved on. I'm still in this protection domain, but now I've got this new capability table, having done my making. I then do, an enter. When I do the enter, what was my A table pops up in this guy's address space as his N table. So if I preload this with some capabilities for things I want the file system to work on, those turn up as parameters in that address space. And so they can work on them. Perhaps at the point I obeyed the enter instruction, I was at P3 1024. That gets remembered on the C stack. I start executing at P00 in the new protected procedure. It does its thing. When it can only access its own resources and the things I've explicitly passed it. It has no access to any of my other resources, so we've got the protection that we wanted. When it's done its work, it does a return, and that end thing disappears from this protected procedure. That procedure is sort of dead anyway because the flow control has come back. I resume from where I was, and I've still got my A table, and so if this procedure had put some result capabilities into that A table, it comes back here as well, so I can get results back. And so that's how you could pass things back and forth in protection domains. And if this procedure itself then returned back to whoever had called it, the C stack pointer would go back, all the A's and N's would disappear. And so as you work your way back to whatever the protection domain was that the process started in, that C stack will clear. So the address space you had in those protection procedures, I've talked about P, I, and R. Typically the way we use them was P contained capabilities that were common to all instances of that protection domain in the system. So if the protection domain was, for example, the directory manager, the capability for accessing the disk in the P segment, and every instance of that protection procedure and every user process would have identical P segment, all the library, algo library segments and so forth, the program code will be shared across all the instances of the directory manager in the system. The I table was used for things that were common to all instances in the same process. In practical terms, that was very rarely used, actually. And the R table was used for things that were specific to a particular instance. Now, where that might arise is, suppose I was working with 2 or 3 different directories in the file system, my home directory and the development directory. I'd hold a capability for each. Each would be an enter capability to the directory manager, but the difference would be my home directory with one capability with the home directory built into the resource descriptor. The development directory would be a separate enter capability with the development directory built inside it. And so the 2 directories were kept isolated from each other. I've talked about the A and N tables. The A stood for arguments, surprisingly enough, things passed in by the caller. N was this new table, capabilities passed on or results to go back. We also typically made table 0 global, which was capabilities available to all domains in a process. And what you might typically have there is, for example, the user login name and the job number and the stuff that might be of general interest to everyone. And everything in the G table was generally read-only. So that was kind of the memory architecture. The magic piece of glue that held it all together, that I'm going to kind of sweep most under the carpet, was a thing called the process base. Every process had one. It was set up by the ESP instruction, and it basically told the microprogram where to find the descriptions of the capability tables in the resource list, an area to dump registers, information about how to go back up the hierarchy, various dump areas and fault information, and pointers to this CStack for enter and return instructions. But it's all full of mind-boggling detail that's not appropriate for this presentation. But with the process base, the CStack and the resource list, you had a complete description of the process. The operating system was fairly straightforward in structure and achieved its goals in getting the separation of privilege. There was a master coordinator at the top level that knew about processes, knew about capability management for its sub-processes, knew about inter-process synchronization, handling messages, and trapping faults coming up from junior processes if they had a memory violation or an access control violation. There were a number of system processes. They did things like real and virtual store management, looked after devices, looked after the file system, and did spooling. Though there was nothing special about them as processes, they were just processes, but they had useful capabilities, like the ability to access buffers to the disk, and certain ends of privileges to call things that users didn't have. And then there were the user processes. The only thing that was distinct about a user process was it had an initial protection domain that was called startop, which might have been a name borrowed from Titan, I'm not sure. And that essentially found a terminal, a teleprinter, and ran the login program. And when you logged in, gave you the command line interpreter, so you could start running a user program. Now, all the description I've given so far has been about memory protection by using capabilities to describe segments and capabilities to describe protected procedures. We learnt, as we built the operating system, there were other kinds of permission we wanted to store in capability tables. And we called them software capabilities. They were capabilities that could describe things like inter-process message channels. So I could pass you a channel so you could communicate with one of my buddies. And that wasn't a hardware thing, it was a software thing. If devices wanted to give interrupts, we needed to be able to pass the privilege of being able to talk to a device to deal with conditions. We obviously had a file system. We needed a way to represent objects on disk. We needed a way to represent memory segments that had been swapped out. We needed a way to represent protected procedures that weren't in memory. And so essentially, we took advantage of the fact that there were spare bits in the capabilities that the hardware understood to steal them. So the hardware would say, I don't understand this, and then the software could take over, pick up the fault that it was an incorrect capability, and interpret it as one of these software capabilities. The downside is this wasn't very extensible. We could only use the bits available, and so the set of software capabilities was essentially predetermined by the operating system, and users couldn't invent software capabilities for things that they wanted to manage resources. Given all that, we then built the environment that the typical user program ran in, and what you would have in your G segment is essentially enter capabilities to a whole batch of systems procedures that acted as gatekeepers into those operating system processes, that made sure when you called them, you were doing things in the right order, you were passing things you had access to and do checks and so forth. I won't run through them all, but for example, there was a store manager that you could go to allocate memory. Please make me a new segment. Please touch this segment so it's pulled into memory. Please flush this thing out to disk. If you had a segment that was very large, you could actually operate a window on it, so rather than swapping in the whole thing, you just brought it in kind of section by section. The directory manager looked after access to the file system. Please give me a capability for the file called Fred, and touch that. An input-output controller, protected procedures that wrapped up I/O streams, and various other more kind of arcane things that I haven't really got time to go into. The whole structure of the operating system was set up by a program called Sysgen, which is the thing I wrote in my first year as a research student. And what that essentially had to do was build the bootable image that had all those capability tables and resource lists laid out and wired together in the right structure, so that if you loaded all that in memory and the microprogram jumped to P00 of the master coordinator, it would just pick up all that data structure and you'd have the operating system. In fact, the boot was in 2 phases. We booted a static image where it only had the resident parts of the system, and that kind of brought itself to life, found the disk drive, and then started swapping in the bits that were in the virtual memory system on the disk. Obviously, we tried to minimize the resident portion as the way in which it worked. And the operating system structure, therefore, was rather than layers, entirely a directed graph. It was all about who had capabilities for who, as to who could pull who. And there were certain relationships between here. The directory manager could certainly talk to the internal name manager, because it had to map textual file names to the actual disk objects. And essentially that's a mapping from text name to internal file name and so forth. So quite a complex dependency structure, and the only way in which you could really understand that as a user is if you looked at the input of the Sysgen program. That's where the true struct system revealed itself. And it worked very well. It was very modular, everything had minimum privilege, and the system basically ran. So I think I will skip over that slide. I'm going to slip over the file systems, I've got too much there. How the machine looked to a microprogrammer, this is the micro architecture. You had this 4K 16-bit micro store, essentially arithmetic and logic unit, one central data register. You had the B registers that the machine programmer saw. You had 16 internal registers that were available to the microprogrammer, and you could write micro instructions that would operate on these B registers and A registers, put them through some function of the ALU, put them onto the D register, and potentially also route them out to the store or the floating point units, or route them out through to the memory of the machine. That was all quite doable. And you also had a hardware instruction decode, and so you could access the operations code of the current instruction. You could access the address field of it, do manipulations. So like all Cambridge machines, the instruction decode was called stage 1. The term actually dates back to EDSAC 1, as I've been discovering, so we've been building EDSAC 1. And the microsequence, increment the program counter, which is B15. I.fetch says route that through out to the store as a fetch and execute. Wait for the store to bring back the data and put that on the D register. It turns out as a side effect, other things got loaded. The microprogrammer's world is a nightmare. Everything has side effects. Not every instruction you want is there. There was a magic thing called the V-store, which looked like an addressable memory, but actually gave you access to various flip-flops around the machine. And that let you access internal state. You could write to some of those and change internal state. And so all kinds of chaos could result. And some were widely held by research students to have the catch fire option associated with them. They just leave things open circuit and the machine would fail. So you fetch the data back from store, you've got the instruction, you fetch, if it's a kind of instruction fetching from memory, you do the index register calculation, fetch the data. An instruction intervene here from another piece of memory called the function memory, where you write the magic micro instruction that completed the user instruction, and often that could be a single instruction, or it could be jumped to somewhere else in microstore that had a long-winded sequence that did all the hard work for you. That would do the calculation, you put the result back in store, and then you do a restart that will take you back around the loop again. So this is the kind of world in which the microprogrammer lives, the register transfer language. The interesting part of the hardware, outside of the floating point unit, which remains a mystery, was the capability unit, which was essentially an associative memory that was designed to speed up that translation of capabilities. If you imagine every time you touched a virtual memory location, the hardware had to run up all those chains, do all those calculations. It would have taken forever, 20 store cycles for every one the user intended. So what the capability unit was supposed to do was essentially cache that stuff. And it was a typical cache. You had two fields that if they matched the segment and offset part of your capability, you get a match that will tell you the absolute address, the size, and the access bits. We could check the address you sent through was consistent with that and allow the store cycle to proceed. So at the micro level, we always sent the translated address out to the store and the data came back. The capability unit ran in parallel and we'd shoot down the memory transfer if we decided it was inappropriate. And that way we got an overlap between the two units. Now the problem with that kind of structure is every time you switch protection domain or process, you'd have to flush all this because the address space changes. And so the trick was there was a small 16-way table called the TGM, and effectively what you would do in this is put for each capability table, you put in this a set of keys such that each different protection domain had a different key, and in the associative part here, you put the key that corresponds to the particular protection domain that owns the capability. And so when you switch process or you switch protection procedure, you just had to update this simple table, and then things could remain in the cache, but they wouldn't match unless their tag matched the keys you put in there. And so that gave you a slightly faster lookup. That meant protected procedures were very fast. They took about 50 regular instruction times because very little had to change in here as you went back and forth. We just updated 3 entries in the TGM for PI or 4. You have to do the AM nonsense as well. Just updated those. A process change is a bit more expensive because you had to deal with a whole lot, but you never had to flush the entire capability unit. This was 64 ways deep. If it had been something like 1,024 ways deep, it would have been big enough. And again, that was all built out of discrete logic. We just took too long. So let's talk about the physical electronics very quickly. Built using Texas 10400 series integrated circuits, all TTL, wire wrapped. Each functional unit on the machine was built as a vertical page, and the pages were split with the logic in the inside and the wiring on the outside. It had an over-engineered power supply unit. Essentially, bits were borrowed from Titan before switch mode power supplies. So their approach was to make more current than you needed and pump it out through what was essentially a bar of electric fire at the back if the machine didn't need it. And it was, because it had the potential to put lots of current through the machine when not desired, there was all sorts of clever multi-stage protection whose main role was to stop the machine ever working. Most Monday mornings, it would get the engineer out to disable the power protection system so they could turn the damn thing on. And lots of lights and switches to enable debugging. It's really wonderful. And apart from the power supply, actually very reliable. So I got some pictures. The machine survives in the computer lab, bit of a paperweight. So here's a vertical page split. There you can see the logic inside in chip holders. There's the back wiring, all wire wrapped. Cambridge approach to wire wrapping is you add the 2 pin numbers, modulo 8 and then modulo 10, and then that tells you what colour wire to use and the resistor colour code, and then you've got a visual check your wiring is consistent. Quite a nice scheme. We're not using it in EDSAC because the EDSAC pioneers hadn't invented it. We invented it for CAP. That's the infamous power supply, which I'm pleased to see is full of cobwebs these days. I didn't photograph very well. This is the front panel, and given where the machine is located and how glossy the surface is, it's actually very, very hard to take a photograph that you can see and not have your own reflection in. So I'm not going to take you through all the switches, but be assured there are lots of them. This was the main control panel. You could inject micro instructions, you could inject macro instructions, stop on all kinds of conditions, monitor everything, slave memory, store control. All these lights told you a lot. That was the floating point unit. My tour de force was to learn enough about how this was internal, had its own internal microprogram that Wheeler kept to himself. But I did manage to make one bit move down and up and cycle round by microprogramming it, and not by using any little number calculations to quite goosey the thing. And so that's the hardware of the machine. So very quickly, the project timeline started in about 72. A lot of students proposed architectures, and a guy called Robbie Walker essentially, I think, designed the architecture that was selected. Certainly he wrote the microprogram for the dominant architecture. David designed the machine. In the design automation was done on Titan, in the case of the previous machine designs the next one. The lab workshops built it. 75 to 78 was when most of the operating system was written, led by Roger, who wrote off the code, and with a research assistant called Andrew Birrell. who had come to him from the Admiral 68 project. Andrew, still very active, he works in Microsoft Research. He did network capabilities and network objects, all that kind of stuff at Xerox PARC. So went on to a fine career. Most of the Cambridge students went on to fine careers. It was a good project. And a whole batch was wrote a capability handling operating system called Chaos, and it was. And I did the SysGen program. By the time the system was running in about 78, it became a departmental machine. It ran BCPL and Admiral 68, the two popular languages at the time. It became essentially the development environment for much of the Cambridge Ring world. All those microprocessors, the cross assemblers and things ran on CAP. It was amusing how many BCPL programs that had been ported from Titan to the IBM 370 that came to CAP exposed memory violations. So none of those machines had sufficiently good memory protection, and many of them had the useful convention that location 0 contained the constant 0. Well, CAP didn't. And it turned out that most of the BCPL systems kind of assumed that. So BCPL had to be slightly updated. In that role, it was displaced by the processor bank as that came on speed, and Martin wrote a little single-user operating system called Tripos in BCPL that ran on those machines, and they essentially displaced it. Bjarne Strustrup was a PhD student, actually more in this kind of period, 75, 78. He was exploring the performance characteristics of operating system structures, messages versus procedures. He wrote all that in Simula, but unfortunately his program got too large to run as a job on the university mainframe. They only had the teaching Simula system, not the production version. So he translated it all to BCPL and ran it on CAP. And to run that simulation, he needed a coroutine package, so he wrote coroutines for BCPL. To convert his Simula into BCPL, he had to write an object-oriented language to lower-level language translator. And when he left the Cambridge Computer Lab, he went to AT&T, and his first paper was coroutines for C. His second paper was C-Front, which is the ancestor of C++. So if the computing service had had a big enough Simula compiler, he wouldn't have done this, we would have spared C++, and we'd all be using Simula, which in my humble opinion is a much better language anyway. But there you go. After that, I wrote a new operating system, explored some new ideas. There's not time to talk about that, but essentially it was an object-oriented operating system. We scrapped the modular one, we used all the ring stuff, we put some modern semiconductor store on the machine. We don't actually know, and there are people who used it still in the lab, but we can't work out when it was actually turned off. We suspect it was left off after a fire in an adjacent department. There was just no reason to turn it back on, it might have been smoke damage. And it sits there as a static exhibit in the Gates building to this day. My evidence for the timeline, in the front panel of the machine still are the punch cards that have the dates of the system builds and which key switches run which system, and that's my fair handwriting. And the last dates are all 79 in the bottom of these. After that, it just sat around and did its job. So, quick evaluation. Well, it worked and people used it every day for 8 years. That's a pretty good success for a system. It was certainly a key resource for subsequent work. In terms of a capability machine, it wasn't a success. None of the early capability machines really were. First of all, you've got to challenge it. If I've given you a permission, how the hell do I get it back when I change my mind? Because it's gone. It's copyable. Now, you have to design the system with that in mind. My Cat3 system had a way of dealing with that, but it was a lot of complexity. It's kind of the analog of what in the access control this system is the challenge of how do you represent users you don't know exist yet. It's a wildcard thing. The enter sub-process instruction was very slow. It was about 200 instruction times. That made inter-process communication quite ponderous. By the time you got into the coordinator and back out again and bounced around a few times. Because we had that local naming architecture, there was a lot of address translation and validation had to go on if you move things between processes as opposed to between protection domains. And the process hierarchy was never used practically, so a whole lot of energy in the microprogram was wasted. Enter was about 50 instruction times, which is pretty good actually, because of the amount of work that has to be done. But it mitigates using it at the granularity of procedures in a programming language. And so they had to be quite chunky. The real Achilles heel, I think, was segment swapping. It was really inefficient relative to a paged architecture. And segments have got quite large, particularly writing high-level languages that produce huge amounts of code. And in 1056K, it was a huge amount of memory in 1970. We were very profligate in how we wrote software. And so we had big things to swap backwards and forwards. Roger and I used to, every New Year's Day, come in and write a new real store manager. And they're all as bad as each other. And the last one just threw segments out at random, and it actually performed slightly better than all the others. The real, I think, trap was that writing the operative in ADL68 actually removed many of the problems it's supposed to solve. By the time you got the ADL68 compiler to compile your program, you've read it so many times, you knocked all the bugs out of it. And so we very rarely had capability violations. But having written a few assembly code programs and run them on the CAP, if we'd still written the operative and assembly code, but no one did by 1978, we would have very much valued having that architecture. So it solved the original problem, but the world had moved on, the original problem wasn't the problem anymore. Great shame. I think I covered most of the quirks, and I'll leave some of these to questions. If you're a microprogrammer, you have to understand Wheeler octal. Wheeler octal has digits 0 to 9 and letter J. And I'll answer questions about what that means in a code that's supposed to only go 0 to 7. I mentioned the one-page CAP summary. I didn't mention the cooling system. If I jump back to the pictures, you see this copper plate at the bottom. There was a huge set of fans underneath the machine that blew cool air up inside the pages. As you swung these pages across on the front of the machine, I need the main picture, essentially the pages will swing from side to side, so you can get from one to the next. This vane would magically move, pulled by a little bit of string of microswitches, to make sure there was never this gaping hole in the middle that all the air would escape from. And most visitors, when they came to the CAP, didn't want to say anything about capabilities. They wanted to see the moving vane and hear it go click clonk. The Hartley Memorial canopy, we lived in the old Titan room and the IBM mainframe was above. David's operation had a water-cooled machine, and occasionally it would leak. It would leak through the roof onto our floor. And so we suspended a large panel of plywood from the ceiling, larger than the CAP, to keep any falling rain off our machine. I wanted to have gutters and a water butt and pretty flower baskets, but overruled by Roger. And I always called it the Hartley Memorial canopy, but David, I think, wasn't very happy with that. And I haven't got time to talk about the file system protection. There were other capability systems. Plessy intercepted an early version of the CAP design. They essentially had index registers that could contain capabilities rather than all that address mapping. That's a much simpler thing to build, but you've then got the register allocation problem for index registers in the address space, as opposed to just having an address space you can use. But given they were entirely writing embedded systems, I think Plessy System 250 mostly ended up in the Talmadge military system. They were writing an embedded system, they could cope with that. Intel did a capability machine, the IXP432. It never, that's the mask of it. It never really got to be very popular. If you try to use it, it was extravagant in its use of memory. I challenged Intel about this on their architects. He said, we do sell memory chips as well, you know. Probably the most successful was IBM's System 38, which that is a picture. System 38 is what IBM's Future Series, or Future System, turned into, which is the thing that ICL was sweating on when they did New Range. They had to have a rival too. IBM had abandoned Future Series, but the guys who did it built this little departmental machine. And it's a capability machine, and it works quite nicely. I did a whole batch of new things, and there are a whole batch of people who try to do capability systems in software, but they're just too slow and too inefficient. So, impact. Looking back, CAP communicated a lot about how to build modular operating system structures, and that has been an ongoing academic research topic since that period. Although I think it's fairly well mined out now, with ideas like microkernels. Windows NT has a microkernel, for example, and various networked distributed operating systems, of which Mac OS is the example most of you will be familiar with, and you won't even know it's a distributed operating system. But there you go. We built one on the Cambridge Ring. I built a success system called Mayflower. Most of my students who worked on that were the group who built most of the Java stuff for Sun. They all went across there, and there's a definite flow of ideas. As research students at the time, this is actually the last bit of that Beano cartoon I showed at the beginning. The last slide shows a rather worried-looking research student saying, but what of the future, am I employable? Because we could see that the writing's on the wall for capabilities. Where the hell will we get a job writing an operating system, as all the British computer companies were going out of business? Most of us fortunately seem to be finding worthwhile things to do. Protected procedures are back in vogue. It's called sandboxing in browsers today. Virtualization, of which there's a lot going on in all that capability architecture, is there, particularly with trying to carve up large servers and smaller machines. Cryptographic capabilities are everywhere. It's how you pass privileges around in the network, SSL, all that kind of stuff. And if you add all that up together, you've got cloud computing. And so CAP was an early example of cloud computing. It was in one box. with a bit over the top to keep the rain out. But when it became part of the Cambridge system, it was a processor server in the way that a modern cloud data center is doing that job. I'm probably stretching this story a little bit to get there, but hey, project I'm very proud of. Could it be restored? And the answer is it remains. No memory, power supply is a nightmare, it's full of electrolytics. We've lost the binaries for the operating system, but we have all the sources, but we don't have, and we have the source of the Algol system, but no binary version. But there is a guy out there who keeps Algol alive on PCs and has a more complete implementation. So you could potentially rebootstrap Algol 68C via Algol 68G, regenerate the binaries, and you could obviously write some kind of simulator. But you've lost the Cambridge ring and the ring services, so you have to emulate all that lot in some way. But the ring interface is very simple. So you could program up the rest of the universe on a PC and then connect CAP to it, if you wanted to. So you use Algol 68C. You could certainly, I think, fairly readily down that path, run CAP user programs in a CAP-like environment to recreate the user experience in the crazy file system. You could then go down to an instruction level simulator and boot a sysgen image. You don't have to write this huge emulator. You could possibly then think about re-making the CAP hardware. It feels like a heck of a campaign. I don't really have the stomach for it. I'm busy building EDSAC. Maybe when that's done. Thank you.
Thank you very much for that informative and entertaining talk. And I'm sure there are lots of questions and contributions.
Tell us about the octal.
Wheeler octal, right. 0 to 7 do what you expect. They give you the standard 3-bit fields. 8 gives you 0 as a single bit. 9 gives you 1 as a single bit. So if you've got an instruction format that's a mixture of 3 and 4-bit fields, you write the 3-bit fields as an octal number. The 4-bit fields, you write the octal number plus the extra bit you want stuffed on the end. And what the J says is essentially it's left aligned rather than right aligned. So if you want to set the top bit, that's J1. Very obvious and very clear, very easy to write an assembler for it. And Wheeler could think and do mathematics in Wheeler octal. I can't do maths in Wheeler octal, I do maths in octal octal.
Just an observation, I'm James May, worked on the John Iliff's machine, basic machine. The machine only used the tags in its registers and on the stack. The rest of the capability store was part of a hierarchy in store, very similar to the PP250, and quite a few team members moved to the PP250 project from the experimental basic language machine. The experimental basic language machine was sadly built on with a reliable power supply, but the rest of the machine was not. And we re-implemented it once on on more modern hardware, but we failed to sell the idea to the company. Thank you.
Everyone else ask a question.
First of all, out of interest, last night I dug out my little monograph on the basic machine that's just been referred to. So if anybody, that little series of monographs.
The Elsevier series.
Yes, that's right. That's written up in there, but there's no reference to CAP, of course, which is one way down. I was interested to see the reference to the Intel 432, just on one of those last slides. Because the only time I ever met that was when we were designing the Ada language, and people were thinking of using that chip to support Ada, which seemed to solve exactly the same problem that Algol 68 solved on your CAP machine. It took away the need for it. That if this 432 chip was good at strong typing, it removed the need to check typing, and Ada does the same. You're killing the same problem twice over.
Yep, I agree.
So maybe that's why the chip never went anywhere, I don't know.
Maybe that's why it went anywhere. There are a number of things wrong with the 432. They went for a bit-aligned architecture, which made the execution very slow, partly because it was extravagant in memory. They then decided they ought to make sure they could still pack things in more. So having made it bad, they made it worse. That didn't help. They were thinking of kind of embedded applications, and yes, people were in that world. You've only got one program, you can get it right. And really, for ordinary users, by that time, people were using Fortrans, Algols, whatever. They didn't want, no compiler writer wanted to play with this stuff because it made their heads hurt. They wanted it all by verification or by designing yet a more complicated type system, as they still do.
You mentioned at the start that your previous machine had only got 16K of memory. It's worth mentioning it's only 18 bits as well, not 32.
Indeed. That's really a matter of precision.
I'll come to you, Devon.
A little facetiously, did you keep the memorial canopy, and if so, may I restore it?
No, because it was just a large piece of plywood hanging on 4 wires. And it was left in the old building when we went.
Oh, was it? Like all bad things in life, I completely forgotten that.
Indeed. I remember we teased you mercilessly that many of us would meet in 1 or 2 Cambridge eating and drinking establishments at lunchtime in the evening. We were always teasing David about his machine needing a napping. And so
It was a bloody good machine.
indeed.
Dan Hayton. Interested to see that you included the System 38 as one of the useful derivatives of it. Does that apply?
Sold?
Yeah, does that apply to the AS400? I mean, was that a direct descendant in the way in which?
I'm not knowledgeable enough about IBM machines to answer the question.
I mean,
if the AS400 is an evolution of the 38 and
Yeah.
runs its programs, then the answer is, I guess, yes.
Yeah, well, that was one of the most successful machines sold by IBM.
Right.
They sold loads of them.
Good.
God, you've stunned us into silence.
There we go.
Oh, yeah.
You mentioned about C++, and that made me think that most of the operating systems nowadays seem to be in C rather than and that presumably, as the friend was saying about C, all the disadvantages of assembler language with all the problems of assembler language. They seem to have lost the sort of, I mean, that gives you all of the disadvantages. You don't have the protection of having a strongly typed language, and you don't have the protection of the underlying operating system preventing you doing things. So most of the machines since then seem to have sort of rather gone downhill until I suppose very recent times with the couple of levels of protection.
Yeah. Mac OS is, more of it is in C++ than in C. Windows slightly more is in C than in C++. I think what happened was, with all the kind of research on systems structuring, people worked out how to do clean interfaces rather than just writing monolithic programs. And so inside Windows NT, one bit of the operating system can't just use a bit of memory from another. There are all kinds of internal protocols that are very strongly enforced administratively. Programs I just told you don't do these things, and your team manager will kick your backside if you do. And so essentially rules of discipline based on some of the ideas established as architectural things to enforce essentially achieve the effect. Because CAP was designed to stop bungles, or blunders as Roger always called them. Other ways of stopping blunders was we just policed the people and we restricted how they wrote stuff. And that's essentially how it works in Microsoft. And certainly today, if you're a Microsoft developer in the system, when you submit your code into the build tree, it goes through a lot of checking programs full of heuristics that know how to spot the classic errors, know what all the standard abuses are, and check for their absence. And if one of those is found, you don't actually end up in the build. Your software gets thrown back to you, and your manager gets an email. And that has a quite salutary effect on programmers. And so, in fact, you can turn the checking system off and people still get things right. We did the experiment once. People are very easily conditioned. They think they're going to be hit, so they prepare themselves to be hit. It's even more fun if you send email messages about faults they haven't got, they go looking for them. This is all part of understanding the psychology of the Microsoft development team. Other things going on obviously I know the Microsoft development story more than Apple's, other things going in Microsoft now is all that heuristic being replaced much more by formal verification. And model checking has got good enough. It's not just device drivers. What the model checkers do is abstract the software to a higher level and then check those abstract models against an abstract specification of the system. They can usually, what you get out of a model checking system is it shows you a path through your program that could lead to an error. And then you discuss whether that path could ever actually arise in practice or not. And with that kind of checking, that's what's making the systems more robust. And Windows is somewhere between 60, I forget which is, between Windows and Office, one is 60 million and one is 80 million, I've forgotten which is which. But that's a lot of code for one person to look at chasing down a bug. So you've got to have good modularity, you've got to have good checking tools, people have got to obey the rules. And so all that is done, but mostly administratively, but building on concepts, micro-capability concept and others.
Is that a shame if it's done that very well?
What it means, you're not compromising the horsepower of the machine. And Microsoft always designed its operating systems so that at the time the next release became the dominant release, the machines would be fast enough to run it. Which, if you think about it, is the right technical choice. You design for the midlife of the system. So the early versions would be running on hardware that could just about cope, which is why my advice has always been, never try and put a new Microsoft operating system on an old laptop. You are absolutely paddling against the tide. If you put a new operating system on a new laptop, room with a chance, if you wait a couple of years, you should be all right.
Just touching at straws, I seem to recall that the Mark microkernel was developed at Carnegie Mellon.
Correct.
I wondered if there was any connection with the CAP research students going out there and taking ideas.
Essentially parallel development. In 1972 to 75, Cambridge, Carnegie Mellon, MIT, and Stanford, and Berkeley were all doing capability operating systems projects of one kind or another. It was the kind of the thing everyone wanted to work on, because it all bounced off the operating system structure problem from their previous large projects. Out of the Carnegie work, Rick Rashid built the Mac operating system, and that followed on. Their first project had been called Hydra. It wasn't a success. It was a very complicated capability architecture done entirely in software, too inefficient. But Rick pinched a few of the ideas and used that to build Mac. He started that in about 78, and I first met his research students in 78. Quite amusing, I ended up working for him at Microsoft. It was the end of my research career. And so he had picked up some of the ideas from the Carnegie Mellon route. The Stanford and Berkeley projects never got anywhere. Berkeley built something called CalTSS. There's only one of them, only the people who developed it used it, and they hated it. So they all went and left and started Xerox PARC, so that's probably a good thing actually, because they moved straight into the networking world. And MIT did the re-engineering of Multics to do essentially the virtualization, so they could do security with a ring-based architecture, and that was all paid for by the American government. I think we're there.
Well, you didn't have to refer to the books at all, no?
Indeed.
To prove anything.
In one case, I forgot there one slide where I had a definite wobbly moment. How did that work? There you go.
Well, thank you very much indeed, Andrew. Our next talk is going to be on Thursday the 16th of May, when Dr. Doran Swade, an historian of computing and a founder member of the CCS, is going to be speaking about Babbage and the analytical engine, the first automatic, general purpose, programmable, digital computer. So I look forward to seeing you all then. Thank you very much.